participant, welcome to the 48th session of day 6 Wadla 3.0 on topic recent trends in deep learning and applications. So today we have with us Professor Bapi Raju from IIIT Hyderabad. So he's going to talk about the deep learning applications in cognitive neuroscience. So before starting his talk, so I would like to introduce him. So Dr. Bapi Raju is a professor and head of the Cognitive Science Lab, IIIT Hyderabad. He was a former professor at School of Computer and Information Science, University of Hyderabad. So India during 1999 to 2019, he worked as a researcher at ATR Research Labs, Kyoto, Japan, and as an EPSRC research fellow at the University of Plymouth, UK, before returning to India. He has over 20 years of teaching and research experience in AI, machine learning, neural networks, and cognitive science. He has worked on a variety of intergovernmental collaborative projects such as Indo-French, Indo-Trento in the area of computational and cognitive neuroscience with a multidisciplinary terms comprising computer scientists, linguists, neuroscientists, psychologists, and clinicians. He is also currently heading the healthcare vertical in the DST-funded National Mission for Cyber Physical System Technology Innovation Hub under at IIIT Hyderabad called iHub Data. He has degrees in BE from Osmania University MS and a PhD from University of Texas. So Arlington, USA. He is a senior member of IEEE, a member of ACM Society for Neuroscience and a Cognitive Science Society. So welcome, Professor Bapi Raju, sir. So in this session, so now the session is over to you.
Thank you. First time coming to IIIT BCT, I've been thinking about, especially after I moved to IIIT Hyderabad, I hear a lot about CCT. I'm happy to hear both in-house participants and virtual participants. Today, of course, this talk is slightly out of the standard series of talks, but I think Dr. Ramnarayan's talk made a move. I'm only following the biological applications, but in the cognitive domain. So today, what I want to impress on you is that whatever advances we are seeing in the deep learning domain, it is not that we can use that to advance research in cognitive science and cognitive neuroscience in particular. I'll give you a glimpse of how we are pursuing a couple of questions. Two major questions that I will talk about are the idea of how brain encodes information, how brain decodes information. So there is information that is received from the external world and is represented, and I have a way of decoding this information. How in these two processes deep learning advances are helping us. So what I would like to see eventually is that there is a bidirectional impact. That not only do we learn about how brain represents information, but there may be some insights that we can give back to the deep learning community, hopefully. Right now it has not happened yet, but hopefully to fine-tune the models that make them more biologically realistic. Although currently it is not a line of work. Most important, a lot of people are engaged in tuning and making these models more useful for practical application. So this is first. Second is that some of the advances in graph neural networks and some of these have made an impact on how we understand. So the first one is more general brain encoding, decoding is related to language processing, is what we are looking at. But you can exactly apply the same thing for speech processing, for image processing, how people look at images and understand them. All this can be done. We are looking at language processing. The second one is more basic, where we have brain structure and how does function arise from structure, and can we use some schemes from advances in deep learning to make this question or these models more sophisticated. Two examples that I will give and some challenges and opportunities. Before that, a few minutes I think on what is this whole process of cognitive neuroscience and what are some of the data sets that are available, right? And so in general, we are interested in understanding how neural circuits in the brain are related to cognitive activities, cognitive processes, whether it is perception, memory, and various other cognitive processes, how they are related. This is the idea in cognitive neuroscience, is to understand how brain processes this. We don't have, so the only way to study this is to study patients who have a problem, right? So, but that gives you an external information from the outside. They have problems in speaking, they have problems in understanding language, they have problems in making sense of the visual pictures that they are seeing, they have problems in listening and comprehension. Right, so we get some idea from, and then look at their medical image and look at what area is compromised, and maybe it has some relevance to this process. Right, so this kind of inference is very common, has given us a lot of wealth of knowledge. What we know about how language breaks down is we know from people who suffered either a stroke or other kind of disorder, and then the brain area damaged, and we correlate with what observations we make on the patient. So this is one line of way of understanding how brain functions. The modern method is to apply functional magnetic resonance imaging, where participants are put inside a magnetic resonance scanner, which is used typically to know the structure of the brain or other parts of the body. Here it is used to study function of the brain. It has given us a revolutionary sort of advantage in looking at brain function in vivo. That means the people are functioning and we get a snapshot of the function of the brain every few seconds. And the earlier method is EEG, electroencephalography, which has been there for many decades. Right? EEG has been, but EEG has low spatial resolution because it's an electrode that you stick on the scalp. You get measurement from billions of neurons, so you don't have localization ability. But functional MRI has better spatial localization. So with this non-invasive method, we now have a possibility to study brain function from outside, right? Without really. Of course, the other third method is actually insert electrodes into the brain and then look at the waveforms and study. And of course, we are not allowed to do that unless under special circumstances where people who are going through neurosurgery, if the skull is open because they have to remove certain part of the brain, in epilepsy, at that time people put electrodes on the surface of the cortex and get it, but it's very localized. Or you have an animal model where you actually insert electrodes or do studies on it. Right? So, but that is also limited, especially if you want to study higher order function like speech, and these are not very evolved in other mammals that you can study. Right? So, what I'm going to show you is how these functional MRI images, when people are engaged in tasks like reading narratives or listening to narratives or other linguistic tasks, and how the brain activates, can we understand something from that? Right? That's the main. So here is what that process shown, the stimuli, different kinds of stimuli, light, sound, and I think, and there are receptors that receive these signals and then activate the circuits, and the brain activation related to different tasks, visual tasks, auditory tasks, olfactory. So here, the brain activation for a task like auditory task, listening to a story. For example, it activates all these areas. So this is the front of the brain, the back of the brain is bottom, top, and this is the side area near the earlobes. This is called the auditory area, the comprehension of language, and the language processing happens in this area. And so we can now get first-hand information about how brain activates and people are engaged in a particular task. So this is the, so you give this stimulus, for example, this picture of a bird, and the lexical item BIRD is given to the participants. It's a visual language task that is performed in the scanner. Participant is going into this magnet, large magnet, and while they are looking at these images, the brain activity is recorded and it is processed, and you get images like this. Which brain areas are active? The red is high, the yellow is highest active, and so on. Right? So you get a snapshot of when they are looking at a picture and when they are processing, understanding, this case passively looking at this image, and then we ask them to think about what this object is, this concept bird, whatever that comes to your mind. Activate sort of your processing of this concept bird. And now the question is, deep networks and many of these require large amounts of data. So we are now beginning to see the public access to large data sets like this, both the structure and resting state function and task-related brain activity. Right? So there are three things: structure, then there's resting brain, there's no task. You're just in the scanner, 10 to 12 minutes. You either open your eyes or close, and you are just reviewing what happened during the day. This is the typical task given. This is called resting state functional brain imaging. The third is task, where I give you stimuli and ask you to do some processing. So all these three types of data are now beginning to be available in the last, I would say, 6, 7, or maximum 10 years. So the largest, one of the largest one is Human Connectome Project. This is a US-based consortium study where 1,200 participants' data structure is to a structure. Let us not worry about the acronyms here. This is structural images, resting state, and task data. Task data of some 8 or 9 tasks: emotion processing, sensory motor task, some working memory task, many tasks that are of 1,200 participants. So it's a huge, one of the huge data sets that is available, and it's free to download, right? And a lot of pre-processing that is also done. And so this HCP data is one workpath on which huge number of papers are coming. This 1,200 data has been put out in phases. They did 600 one time, then 800, 900. 1,200, I think last year it reached that. The next other one is an aging data set. The other thing that is interesting is when due to aging, there is loss of neurons, there is loss of structure, and some functions are intact, some functions become slow. For example, sensory motor response, right? You give a stimulus and how quickly I process that. This ability reduces with age, you become slower. Right, the young person is able to react with say 60 milliseconds. An older adult may take 110 milliseconds. Right, so there is a slowdown in the sensory motor processing, but there are other functions which may become better. Right, so this gray hair gives you more wisdom. So, for example, people have seen compared to a younger or adolescent, the language processing, linguistic judgments, these are much better. Emotion processing, all these are slightly superior. Right? It's not like hugely superior, but if you compare to say middle age, there is at least the function is not lost. Right? So now the question is, how is it that in the face of loss of structure, you maintain some functions? Of course, you lose some function. Can we understand how brain maintains this stability? And so this is very important if you understand in disorders or diseases due to accident or due to neurodegeneration. If some function is lost, can we use this knowledge to support the loss of function? Right? And that happens prematurely. And for example, due to stroke, you lose speech function or other motor function. Can we support them with this knowledge that we gain from how brain maintains plasticity and stability? So it's a very important area. And again, we have large-scale data set of structure, resting state, and task function in aging. So this data set with 700 participants is done in UK. This is a US-based project. This is UK, where they have stored data from 700 participants ranging from 18 years to 80 years. These are all healthy participants, and some tasks, sensory motor tasks, and other, not as many tasks as in the FCG, but few tasks have been done here also. But structure and this is again a lot of publications coming from this CAN data. Again, this all this data is free to download. You have to apply and state what research problem you are solving, and they give you access to this. The third one is actually a disease database. It's called Alzheimer's Disease Initiative. And this, there is no task because these participants are older. Typically, Alzheimer's strikes an individual after 60 years or 65. So it's difficult to make them put in a scanner and make them do a task. In general, there is no task data, but resting state data is available. And T1 BPM. So this is again 1600. This is an international consortium. Members from Europe, US, UK, all this contributed. And large scale data set, this is an opportunity that we have, right? Where if you have a question and you have a model, you have the data available. And the other last one is UK Biobank. It's not visible here, but UK Biobank. This is a huge 100,000 participants data is available. This is very, they have by far the most diverse data sets that are available, where all this, I was talking about in the previous talk, I asked this question about how do we learn association between multimodal data. They have their demographic information, their lifestyle habits, their blood markers, their imaging markers, genomic markers, all these are available for this. It's actually 500,000, 500,000 participants, they have all the data, but for 1/5 of them, they have imaging data. By far, one of the largest, but of course, you need to apply to access, but this is a great resource to understand. And so, one of the other opportunities, we should create such data sets in India also. If we don't have this zero available, that is as freely available as these are. There are, I'm sure many hospitals have their in-house information, but it has not been curated and made public and lot of things that you need to do, right? So medical data is ethical considerations. You need to anonymize, depersonalize, de-identify. The whole process that these people have done is a little bit too difficult, but there is also another consortium that makes this data available called Enigma. These are psychiatric disorders, about 20 odd disorders that, India, for example, India's bank contributes to, I think, autism and obsessive compulsive disorder, something like that. Right? So these are the data sets that are available. And the problems that I'm going to discuss today give you a glimpse of how we have used this. One is this alignment between deep neural networks and the brain. So you have a deep network that processes language. So there is some process by which it learns to do a linguistic task, natural language inference or paraphrasing, summarization. There are many tasks that now they are very good at. Of course, one question that comes to your mind is how does this process and how is that similar to how humans process? Right? So, and this question has two ways to address. One is I am talking about brain alignment, but an associated question is cognitive alignment. So this is looking at this network from the outside. Just like I observe human, I give, for example, there are known issues that humans face. If you give, ask them to generate, freely generate nouns, right? They know, they are known to generate one category and switch to a nearby category. So this is free generation. I'm not asking you to give all, say, nouns that start with L. This is a task. Free generation, this is used, for example, to diagnose some cognitive disorders. For example, in dementia, they're asked to do free generation, and people know that their fluency comes down and they become more one category oriented. Right? So this is disorder. But if you give it to normal human, they are jumping about, there may be 5 categories there. Suppose I give this task to deep network, how does it behave? And what are differences and commonalities between? So this is one example, lexical decision making. The other type of tasks that we give typically studied in psycholinguistics. Right? We give a reasoning task, a natural language reasoning task, or a grammaticality judgment task. So what kind of errors humans exhibit? What kind of errors deep networks exhibit? Or these representation models, whether these embedding models. So, what is the semantic space manipulated by these models? What is the semantic space that we can glean from humans? How similar and different they are. This is to understand how human-like these representation schemes are. So I have not put that on the slide, but this is one area of concern which is interesting. This is alignment from a cognitive alignment perspective. What I am talking about here is brain alignment. And because I have access to brain data, when people are processing either reading or listening or something narrative, I can now look at what is the activation in the deep network, what is the activation in the brain, how similar they are. So this is one. Second question is more structure oriented. Can we characterize the brain structure and function using the latest advances? For example, we looked at some graph-based representation and how to learn this model. And how, for example, in this, how do we model aging? I remove some structure. What is the breakdown in function? And this breakdown is similar to how what you see in aging-related changes in the normal brain, and what is how do you characterize? Right. So actually there are 3 problems that we are interested. Third one I did put, what is the cognitive alignment between the recent language models or vision models. So right now the revolution is hitting every domain. Right? It is not just about language, vision, speech. Everything is impacted by the truck. Right? So this is the typical data set. I give concept and word, the picture and the word. Right, so this concept, this actually, I should have labeled here bird. This is bird in different types of visual. So this is given, and the second view is participants are given a word cloud, the central concept and the related word, nest, and all this. So they are asked to focus on the central word and how it is related to bird stays in a nest and things like that, those kind of. And this is called the concept plus word cloud view. And the third is sentential. So there's a concept and there are sentences. One sentence at a time appears. The sentences that use this concept word called word. Right. So this in all these three conditions, brain data is recorded in the functional MRI. They are shown this, and you are recording the brain activity. So this is a typical data set. This was published in 2018 by Tadayra and al., published in Nature Communication. And this data set has other things also. Just in the interest of time, I'm just going to that quickly here. Three experiments. Experiment 2 has a concept, a topic, for example, music instrument, and there are different kinds of instruments. There are sentences that are used in this. And there is a topic, and there are different passages. Right? They describe different things about ski and different things about gambling. So different resolutions of language use, right? And the 180 concepts that they have looked at, and in this, some are verbs, some are nouns, adjectives. The 16 participants who went through this, their data is now made available. After the publication of this paper, the whole data set along with pre-processing, everything is made available. So for people to do additional things. So so two major questions one can ask in this, the encoding and decoding. So in the next few slides, I am giving you what does encoding mean? What is the encoding problem? Encoding problem is a problem of predicting brain activation given the stimulus. Now, stimulus can be picture, stimulus can be word cloud, stimulus can be sentence. What is its mapping to the brain activation? Right? So this direction. Stimulus representation to brain activity. So how is this information encoded in the brain? So can we model this relationship between the stimulus properties and the brain activation? The model that learns this mapping is called an encoding model. And the reverse, given the brain activation, can you predict what stimulus they are experiencing currently? It's a much harder problem, much more imposed problem, right? Activation can be related to multitude of things. Especially, you are seeing this, your own personal experience of what your relationship to bird may be different from different individuals. So what is activated and how can I predict? It's much harder problem, but very useful eventually. If, for example, if a person has quadriplegia or something that doesn't allow them to act on their thoughts, they have intact brain, thinking, everything, but their muscles are not active. In that case, you have to decode the information and use this brain-computer interface to do the action. Right? There are some preliminary solutions already people have used for navigating a wheelchair, for example, go right, left. Simple things, but this now research can now give us more complex DCIs in the future, right? So that's the potential for decoding. Okay, so we need to predict basically. So the thing is forward mapping from stimulus to brain activity, from brain activity back to stimulus. There are two different problems. This decoding model, this encoding model. And typically, how we do that in this is one of the early papers from MIT, where they have explored this sort of encoding model, where they have taken the stimulus material, put through a deep learning model, and the internal representation, hidden unit activation from this model, and the model is a black box. Now you can replace it depending on the what has been put out. Right, you can replace from a CNN all the way to transformer. Right, you can get these activations, and then the stimulus given to the brain. This data is available to us. It's the same stimulus given to humans. Yeah, fMRI. So brain activity, you can pick the top, say 5,000 active voxels in different regions of the brain. Now I have 5,000 brain activation vector, and you have this representation vector from the deep learning. Then you learn a mapping between these two. And so this is the input, and this is so in encoding, you are learning mapping between this given this representation of the stimulus. Can you predict the brain activity? You are learning this model. So people have tried all kinds of models, starting with very simple ridge regression model. You have a vector X corresponding to the hidden unit activation. Now which hidden unit to take? You can try all of them, see which one gives you the best mapping, alignment, predictive power of this. And people have seen, typically in most of the networks, the middle layer seems to be giving much high alignment to the brain activity. So this ridge regression model, and this model parameters W that generates this this predicted activity Y hat. Y is the ground truth actual activation. Y hat is the prediction, and all this. So you have the fMRI board response. Board, let's not worry about this, but this is an activity. It relates to oxygen level changes within the blood. That's why it's called bold. And so that activity over time is modeled by this very well by this representation. Right? So and you can look at how well these two correlate. There's some correlation, various other ways to measure this time series similarity and predicting the activity in this voxel over time. It could be average activity, in which case I only have one number here, one number here, and then how well this predict for different stimulus representation. So I can take a part of the data as training data, learn this model parameters, and then test it on and do cross-validation type of the typical machine learning approach. And this approach has been used, right? So you model this training and evaluation using cross-validation, regularization of these parameters chosen via this the standard cross-validation approach to learn these parameters. And so that is encoding model, going from stimulus representation to brain activity. The other is decoding. Decoding is that I have the brain image corresponding to the stimulus. For example, I'm looking at apartment picture in the word apartment. It activates certain brain activity. And I take the informative voxels from this brain, and now I need to predict the actual, let's say the text vectors, blog or any of this word to vec or Roberta or any representation that you want to. So you want to predict the dimensions of this representation, the 768 or something for but any of those representations have to be predicted from this brain activity. So this is the text embedding semantic vector associated with apartment, and you want to learn a mapping between these two, the voxel vector and the text semantic vector. This is the deep people have used starting from rich regression learning models, and then this alignment is evaluated using multiple measures. One of them is again apply this some of the a subset of the data used as training set and test set, and there are pairwise and rank-wise accuracy that are used in. So pairwise accuracy is if I predict a text vector, how close is this to the ground truth, and how close is this to the others, and I can look at the pairwise average accuracy as well as the rank of what I predict. You know, if I look at all the other text semantic vectors, does it occupy the top rank within the possible alternative text vectors? What I predicted occupies the top rank. The rank accuracy is another measure that is used in order to evaluate these decoding models. So this is from Pereira paper 2018. So what is shown here is there are pairwise accuracy is what is plotted. These dots are the individual participants. There are 18 of them, and this is the average. The bar is the average, around 78, 70, 77% accuracy over all the sentence view, picture view, word cloud. So some of them, picture has the highest, sentence has the next highest, and word cloud has the least. But all of them are above chance level. There are quite significant accuracies of these. These are the average results on the test set. And so decoding, here what decoding means is that I give you brain activation and I predict which of the words, right? I'm generating the text vector, and this vector occupies, this has the high accuracy compared to the ground truth, right? So you also have rank accuracy, which is what is predicted, the y hat that you predict. What kind of rank does it occupy when you compare with the rest of the sentences in the database? So typically, the rank accuracy is also very high, 80% for experiment 3, which is all sentences, paragraphs on topics, and so on. Right? The average accuracy for all the 18 participants. So this sort of model, and where are these voxels distributed in the brain? I don't have a brain picture. Yeah. So this is the front of the brain, back of the brain. This is the visual area. This is the temporal lobe, which is typically involved in language, and the inferior frontal region also involved in language production, language comprehension. So you see that most of these, remember, they are looking at a picture. So visual area is also active. What are different areas where these informative voxels come from? Language, around 22% of the voxels are from language area, and visual area another 20%, and so on. So this is not like random voxels in some other areas, but relevant areas that you would imagine that the brain regions that would be involved in seeing, understanding language, and those kind of areas. So this Pereira paper has set sort of a benchmark for a universal decoder. So remember that this decoder that is built, it works across tasks: picture view, cloud view, sentence view, passage view, all it works across these. capable of extracting representation of mental content from linguistic material. So what we have done is to follow up on this using the same data set. We did two tasks. One is visual linguistic brain encoding. It explores image and multimodal transform efficiency for encoding for brain encoding problem. Right. So this is a decoder, but we use this data set for encoding problem, which is predicting brain activity from stimulus material. So we have a way of representing this multimodal. Remember this, you are seeing a picture and a concept. So picture can be put through image processing module, like a CNN that does an image classification. You extract representation from that. And you have language processing done through language. And you have multimodal vision and language models, right? That combined. So we use those representations in order to learn this encoding model. And so I don't have the results here, but you can look at this paper. The other thing that we did in the same year is multi-view and cross-view brain decoding. So the idea is that when you are looking at, when you have representation, when you see a picture, right? Unlike machine models, human cognitive system has the ability to evoke multimodal activation. I remember the smell of it. I remember the taste of it. If it is a good item, and I activate the episode where I had a good time going to a restaurant and eating this in this particular with other friends. There's emotional activation. All of this multimodal activation is default. It's not something that you plan. Right? Of course, you can focus on certain things and amplify. So let me recall the joy I felt. Right? Then maybe I block some particular activation. So what we thought is that this activation that you see, you could actually put it to multiple uses. Can we use this to do multi-view decoder? Right? So from picture to sentence, can we use this activity from picture to predict sentence, to actually construct a sentence, to actually construct a word cloud? And can we build system that use brain decoding to automatically describe what a subject is watching using keyword sentences? So this is a decoding solution. So brain activity, you take to generate captions for picture. Or you're seeing a picture, but I generate a whole sentence describing the picture. Is it possible? And we say that our hypothesis is that the brain activation is rich. It activates, and it's only a matter of how you utilize it to reconstruct what they are not currently seeing, perhaps what they are imagining. Right? They might be. It is possible to do that, is what we have shown with different variety of tasks. We did keyword extraction, we did caption generation, sentence generation from brain activity. So the last one in this line, which I'll give more details, is to use transformer-based representation. Right? This, I thought you have gone through this in more detail in this workshop since first day, where you had this this embedding, positional encoding, self-attention, cross-attention. There is this output generation, the decoding part, encoder, decoder part. So you can use this sort of rich model representations from this, and we did a recent one where we looked at task-specific language model and how they align with fMRI activity. So you have a pre-trained bird and just say fine-tuned for different types of tasks. This is fine-tuned on the question answering database or natural language inference. So these are different task-based representations that are learned fine-tuned on different tasks. Paraphrase, summarization, question answering, sentiment analysis, name, recognition, all these different task-based representation. Look at how well these explain brain activity. And it turns out that this paper is called neural taxonomy. Taxonomy is studying how tasks work here in this neural domain. Can task-specific language models have similar predictive performance for reading and listening? Right? So reading and listening are two related language tasks, but are different. Reading, we have visual input, and we have language comprehension. Listening, we are actually getting auditory stimulus and language comprehension. Right? So we have data sets. Fortunately, big data set. Reading is that Pereira data set I talked about. Listening is another data set that's available now for a huge number of participants who are listening to a story, and their brain activity is recorded, aligned with this stimulus, this auditory stimulus. So use these data sets to assess whether task-specific language representations have, how well they align with this brain activity while reading versus listening. And other differences, similarities. This is what is this. This is published in NACL 22, where we looked at reading related, so where participants are reading a narrative, and that representation recovered, taken from task-specific transformer-based model, and use that to learn a model, right? And then you can use these correlation measure or 2 versus 2 accuracy. This is more stringent measure that looks at what I have recovered as a brain activity, how similar it is to ground truth, how similar it is to other activation, right? So just to make sure I'm not generating something actually similar to some other brain activations related to other stimuli. So this penalizes for any similarity with other brain activity related to other stimuli. Right? So this accuracy is more stringent than simple Pearson correlation. Look at all these measures to look at both in reading and listening. In this, there is a listening task. So acoustic features are what we use. Right? In this case, we are using textual features, but from the narrative that is basically listened to. And what this complex graph shows is different areas: language, left hemisphere, right hemisphere, vision, in different aspects of vision, scene, processing, object, face area, body area, and overall vision area, and task positive areas, positive area. What this is showing is the 2v2 accuracy. The if you take voxels from this area, object part of vision area, how well different task representation, how well they do. In this case, for example, this, which is the co-reference resolution model representation taken from that, I have a higher predictive value for vision area. Right? So in the vision area, co-reference resolution, as in the language area, also has this activity, but the second next is NER has a higher activity, and so on. During the listening, the reading task. So reading, where people are maybe paying more attention to the grammatical structure and also resolution of there are sentences where it says I have seen this this elephant and it has, right, and then I have to resolve it is this. So there's all this processing that is happening. Maybe those brain areas have higher alignment with these reference resolution type of representation. So syntactic. So subregions have these subregions have higher predictivity. Just for reference, I've given this brain image. I should have put this in a earlier slide. This is the front of the brain, back of the brain. This is the frontal area called Broca's area, which is important for language production and language generation. This temporal area is important for language comprehension, primary auditory area, and language comprehension area. And this area is supposed to be more important for temporal area for language, grammatical judgments, language understanding, comprehension, all of that. So that's what these different areas that are shown. This is frontal area, these areas, different sub areas in the frontal area and the temporal area. The middle part of temporal area, the superior anterior part, like that. Different sub areas, those voxels, how well they are explained by these representations, is what is shown. And the representation from co-reference resolution have this sort of profile. Right, so this predominantly language representation, this representation that do this basic linguistic processing have high alignment in the temporal area, which is from other studies. It is known that this area is important for different judgments, language judgments. Right? So these are frontal areas here and temporal areas. So in the listening, we have done this profile is quite slightly different from the reading profile. To imagine, so now all these areas, these are auditory areas. These are different areas. The early auditory, late auditory. These have because these are listening tasks, where listening areas are much more active. And different representations now have a better, for example, this paraphrase and natural language inference. Remember, in listening, there is no text. So you have to pass everything online, right, in real time. So there is different profile of activity across subjects in this listening task. So different representations have a higher alignment compared to the previous one, which was 4 different representations, syntax, shallow syntax, all that. So while reading versus listening, there seems to be a difference in how brain is activated. And that's also recovered through different representation. And so this was this paper which looks at task-specific representations, how well they are aligned with reading and listening. Right. So now, in the last few minutes, what I want to discuss is change here and look at structure to function mapping. Right here, what is shown is that there are 2 representations of the information of the brain. The left-hand side is structural information, where slice by slice we have information about which region is connected by fibers to which, and those structural connectivities can be captured in terms of a matrix. If you parcel this whole brain into, let's say, 60 regions, how each region is connected to the other region. Are there fibers? If there are fibers, how dense are these fibers? Some are weakly connected, some are strongly connected. You have a matrix that represents this structural connectivity information. So 60 by 60 in this case, for example, if 60 is the, you can also have 17,000 by 17,000 to have a higher resolution, right? force resolution. And exactly same thing, but here the connectivity is functional. So if the brain is active, you have this response profile in two regions. How correlated are they? Now you can use a traditional Pearson correlation as a measure of how correlated the activities are in two regions. And you again get a 60 by 60 or 17,000 by 17,000, depending on how coarse or how high resolution you are. So you have a 60 by 60 functional connectivity matrix and a 60 by 60 structural connectivity. One thing you can see is that most of what you see here is also there, but there is additional activity that is not simply coming from structure. So two regions are active, not because they are physically connected, they may be indirectly connected to other regions. Right? So all of that is captured in function. There is more functional connectivity than structure can explain completely. It's not a one-to-one relationship. The question is, how does the structure function arise from structure? Is there a way to characterize this sort of function from structure, and can we return a structure from the function? It's both forward and reverse forward. Can we pose and we can put whatever is the state of the art to the service of this, to learn this math. So what we did is we used graph neural networks and graph. Not going into the details, but graph neural networks you heard, and it's a nice framework to look at the brain as a graph where nodes are regions and the connections are strings. Right now, you can look at this graph and look at how activity propagates through this graph, and the propagating activity is the function. So you can learn this relationship between structure and function using this graph feed network that we propose, and we look at how well the predicted functional connectivity is related to the ground truth functional connectivity. The loss here is what is used to optimize the parameters in this graph network. This difference between the predicted functional connectivity and structure. Most of these cases, because they are symmetric matrices, you can just take the lower triangle, upper triangle matrix and try to look at see if in this case if A is connected to B, B is connected also to A. In this case, because you are only looking at the function correlation. And training and testing in this case were done using resting state functional connectivity. Right, so this comes from the structural part of the data set where we have the DTI diffusion tensor imaging that gives you an idea of the fibers that connect to different regions. Resting state functional MRI gives you the connectivity between functional connectivity. And we use this on the XCP data set so now we have made this to 1200 participants. So some part of it is used as training or test, right, in a cross validation fashion. And the average predictive power in graph GC, graph convolution network and encoder decoder. This has slightly higher accuracy general compared to our earlier model called multiple kernel learning model. Compared these both from predictive power, this is the PSM correlation between the functional connectivity versus ground truth is the test set, 80%. Not only does it predict, but it also has similar sort of this AGHM, it's a similar sort of connectivity pattern that it learns as compared to the ground truth. It's not just that it is able to predict the average functional connectivity, but the actual structure the weights associated with different regions also has a similar profile as in the brain. So this is a series of models that we did. This model is also out, the MKL, multiple kernel learning, where we use this again a graph formalism or graph signal processing framework where we have diffusion kernel that diffuses activity from a source to the different target region, and how much of this decay and at what point it coincides with how those two regions are connected. That learning has taken place here. So this graph networks seems to have better both this GCN based and traffic network seems to have better alignment to the structure function. So to conclude, what we see is first is some of the challenges that neuroimaging data is usually very complex and noisy compared to other data sets that you work with, whether it is ImageNet. Most of them are very clean data sets, whereas brain imaging gives you a very noisy data set. This individual variability is also the same. So it gives you the same task, you and I activate. There is some overlap, but our experiences are different, our initial points are different, so the activity profile can be quite different. Individual variability is not the exception, it is the norm, right, in neuroimaging. So data collection, some harmonization in terms of what were the conditions in which they were recorded, what was the machine that it, what was the particular pulse sequence that it, all these seem to inject variability into the measurement. Right? So we need to have methods that overcome these. Other thing is that these are time points. At a particular time point I have taken, longitudinal data is going to be also important. People have started to begin to take this. Same person scanned over multiple times. Right? So is there a inter time point variability on the same task? We know that age-related changes are there, but what is the spontaneous differences? All these are going to be important if you are building models, right? So, of course, the opportunities are quite a few. Exciting times because of this publicly accessible data set of various tasks, and all of our work was possible in the last 5 years only because some people were generous to put all this data. Right? You, even though you have an idea, you cannot really do anything if you don't have access. So that's really generosity. I feel it's increasing more and more, and we should also contribute from our own side. Like Indian brain, I'm sure, is very interesting. You should scan and put a lot of data, especially multilingual data. Right? And there are a lot of unique things. And there are people that can understand language, but they don't know how to read. Right? So, and most of the models, current models of how brain represents language is from monolingual literate Western brain. Right? So I think we are first thing I think essential thing is to collect data and make it available. I think then the knowledge flows from multiple people practice, crowdsource research. So, and this is one domain where data is ahead of theory. A lot of data, but theory is still in the early stages. And it's important. Maybe in order to understand information organization in the brain, this modern deep learning, machine learning can help recover these, get us to the goal of understanding information. So these are some of the colleagues who have similarly an MTech student who then went to PhD. He has worked on a lot of these problems with our students here. The PhD student capability, the students capability. Vijay has now joined part-time PhD. Sushita and Microsoft has been working with us. Thank you.
So thank you very much for your wonderful session, sir. So really your session was very informative, like related to the domain of medical domains, as you know that now it is booming area like everywhere, like so.